Implicit differentiation is really an algebraic technique. Well, it's a calculus technique, but it's of the algebraic variety. In other words, it's a calculus technique that only involves manipulating equations and doing algebra. However, it's not without its geometric interpretation. And to get a more intuitive feel of what these implicit equations actually represent, we're going to, in this video, look at examples of specific implicit equations and their graph. So we're going to start with perhaps one of the simplest implicit equations, and that's the equation for a circle. So you may be familiar with this equation. X squared plus y squared is equal to 1. So this is literally all points on the y plane that are at a distance of 1 from the origin. So this is going to look like the following. There. So basically, here's x and there's y. 1, 1. Right? Because for any point on this curve, we can construct a right triangle. So this leg has length x, and that leg has length y. So the hypotenuse is going to be given by a square root of x squared plus y squared. So this equation basically says that it's the set of all points, or the graph of this equation is the set of all points on the xy plane that lie a distance of 1 from the origin. And of course, this is just going to be a circle of radius 1 centered at the origin. So that's what the graph of this implicit equation looks like. Now you might say, hey, let's solve this for y. And of course, y is going to be the square root of 1 minus x squared. Well, this is a little bit different. This is only the top half of the circle, right? So here we're trying to make y into a function of x. So that function of x would be f of x is equal to the square root of 1 minus x squared. But you're only getting, the upper half, so this portion up here of the circle. You're missing the lower half. So the actual solving this for y, we would get y is equal to plus or minus the square root of 1 minus x squared. So for a given x value, you actually get 2 y values. So y is not a function of x. So this is where people sometimes say that y is an implicit function of x, but that's not good terminology because it's not a function at all. What you can say is that y is locally a function of x. So what this means is if you fix a point on the curve and you restrict your view to some small enough bubble about that point, within this bubble, y is a function of the variable x. So locally, so this is a word used in even advanced mathematics, locally, or advanced geometry, so locally, y is a function of x. That is when we just zoom into a small neighborhood about a particular point, y becomes a function of x. However, we're going to eschew this sort of terminology now to avoid confusion. So y is not a global function of x. In other words, when you consider the entirety of the graph, you do not get a functional dependence of one variable upon the other. So we'll just say that this is a graph of an implicit equation. So the implicit equation cannot uniquely be solved for one variable in terms of the other. See, when we try to do that, we get y is equal to plus or minus square root of 1 minus x squared. So y cannot uniquely be expressed as an explicit function of x. So that's why this is an implicit equation. So the circle becomes just a graph of an implicit equation. And in fact, I have the graph right here. So this is just a graph. It's just a circle of radius 1. And notice I graphed x squared plus y squared is equal to 1. Now let's jazz this up a little bit. So let's do x squared over 9 plus y squared over 4 is equal to 1. and I need to change the window like this. And what does this look like? Well, we'll come back to that in a second. So let's first examine what this equation might represent. So here we have x squared over 9 plus y squared over 4 is equal to 1. It's certainly similar to the equation for the circle, except we have something else going on in the denominator. This is an instance of a more general family of equations. X squared over a squared plus y squared over b squared is equal to 1. So this is an equation for an ellipse. So equation for an ellipse. So to see what this ellipse might look like, well, why is it an equation for an ellipse? Well, it has a very good, simple way to see that. Basically, the x variable is stretched. So x is replaced with x over a. So in that case, it's a horizontal stretch of the graph. So if we start with a unit circle, x squared plus y squared is equal to 1, and we replace x with x over a, we're stretching the graph horizontally by a factor of a. Similarly, by replacing y with y over b, we're stretching the graph vertically by a factor of b. So this should be an ellipse where x is stretched by a factor of 3 and y is stretched by a factor of 2. So maybe something like that. So here's x is equal to 3, there's minus 3, here's 2, here's minus 2. Now the way to remember which way this goes is, well, the x-intercept occurs when y is equal to 0. So starting with this equation, if we set y is equal to 0, we get x squared over 9 is equal to 1, and then that can be solved for x is equal to plus or minus 3. So the x-intercepts are going to be at plus or minus 3. More generally, with this equation up here, the x-intercepts are at x is equal to plus or minus a. And the y-intercept are at y is equal to plus or minus b. So for the y-intercept, we set x equal to 0 because x equals 0 corresponds to the y-axis. So by setting x is equal to 0 and then solving for y, we get plus or minus b. In this equation, the y-intercept would be at y is equal to plus or minus 2 as indicated on the graph. So going back to what we have here, if we actually do the plot, there we go. So the x-intercepts are clearly at 3 and minus 3, and the y-intercepts are at plus or minus 2. Now, aside from circles and ellipses, there are plenty of more exotic graphs you can produce using implicit functions. In fact, if you have a graphing calculator with an implicit function mode, you can play around with this and explore these sorts of functions on your own. The next one is a family of implicit functions. So we have x squared plus y squared minus 2ax quantity squared is equal to 4a squared times x squared plus y squared. So we're going to set a is equal to 1, and we're going to get a particular instance of this family of functions. So this is in general called a cardioid. And we'll see why it's called a cardioid momentarily. So let's go ahead and plot this. So the cardioid equation is going to be x squared plus y squared minus 2 times x squared is equal to 4 times x squared plus y squared. And then to get a good view, we'll go from -5 to 1 in the x, and then -3 to 3 in the y. And usually, okay, interesting. So it's not exactly what I expected. So x squared plus y squared minus 2x quantity squared is equal to 4 times x squared plus y squared. So I have the graph figured out. Setting a is equal to -1, not +1, we're able to get a graph that looks like this. So with an a value of -1, the cardioid x squared plus y squared plus 2x, all quantities squared, is equal to 4 times the quantity x squared plus y squared, gives us a shape like this. So we see why it's called a cardioid. The graph of this implicit equation looks like a heart. So if you look at it sideways, you get something that's heart-shaped. So this would be an example of an implicit equation. So instead of trying to solve for y as a function of x, if, for example, if you want to find the tangent line to this graph at a point like right here, it would be a lot of work solving for y as a function of x, because here we have a quadratic x squared plus y squared minus 2ax. It's all squared, and that's equal to an x squared and a y squared. So there's a simpler way to find the derivative of y with respect to x. Now, since this implicit equation is, you can't actually have there is no functional dependence, y is not a function of x, the derivative dy dx will not depend solely on x. It will depend both on x and y, because as we can see from the graph, the slope of the tangent line is going to be different at this point, at that point, at this point, and at that point. So for one x value, we might have 4 or more different slopes for a given implicit equation. So in order to actually pinpoint the location along the graph that you want to compute the derivative of, you need both an x and a y value. So the only condition on that xy pair is that the xy pair has to satisfy your original equation, which is this equation up here. So for any xy pair that satisfies the equation which defines the graph, you can plug that into the derivative equation and get dy dx for this point or that point or this point or this point or any other point on the graph. So we'll take a look at that in our next video.